Hey guys, so today we're going to talk about the Leucine zipper. First I want to start out kind of talking about the basics, and then we'll get out bigger and talk about what makes up this zipper structure. So initially we have amino acids. Amino acids each have a amine group, a carboxyl group, a hydrogen, and they have a side chain called an R group. So each amino acid has a different R group, and that's what makes it differentiated from other amino acids. So let's talk about how do these bond. So if we have two amino acids, you're going to have the amine group on one amino acid is going to bond with the carboxyl group of another amino acid. So when these two bond, it's what we call a peptide bond. So when you get multiple peptide bonds, so you get multiple amino acids binding together with peptide bonds, it's what we call a polypeptide chain. So you've got this amino acid sequence, and they form a polypeptide chain. So how do we combine these chains? So how do we get these together? What do they form? What do they look like? So today we're going to talk about the alpha helix. So you've got two polypeptide chains, and we're going to have hydrogen bonding to combine these two. So you're going to have a hydrogen bond between an NH group and a CO group on two different amino acids. So this hydrogen bond is going to be in the center of this alpha helix. So you can think of it as like a ladder. So each rung of the ladder is going to be a hydrogen bond. And then how we talked about those R groups, those side chains, those are going to be on the outsides of your ladder. And with the alpha helix, instead of it being just like a flat ladder, it's actually we're going to have some twisting. So every third or fourth amino acid is going to hydrogen bond. So you're going to have this helical structure. So it's going to almost look like a twisted ribbon, if that makes sense, with those side chains on the outside. So now we've got side chains on the outside of one alpha helix. So how do we get two alpha helixes to combine together? So the leucine zipper is what we call a coiled coil. So you've got your one alpha helix that's already a coil. Then we've got two alpha helixes, and they're going to coil around each other. So what keeps these two alpha helixes bound together? So what keeps them together is two different interactions. So in the center of this specific leucine zipper, we've got the amino acid leucine. And leucine happens to be a hydrophobic nonpolar amino acid. So that means that it does not like water, and it is not charged. So we've got a leucine on the outside of one alpha helix, and the leucine on the outside of another alpha helix, and they're going to come together. They're going to migrate towards each other because hydrophobic likes hydrophobic, right? So they're coming together, and they're going to create this point of contact for these this zipper interaction to happen. So you can think of it just like a zipper. So we can coil them together, and then if we want to undo the zipper, you go the opposite direction. So you're going to take it apart. So something's got to be holding it together, right? So that's what the hydrophobic effect of the two leucines is creating. And then we also have this electrostatic interaction. So when we think of electricity, right, we have to think of charges. So on this specific leucine zipper, we've got lysine and glutamate. So these two amino acids have side chains that are charged. So lysine actually has a positive R group, and then glutamate actually has a negative side chain. So what do opposites like to do? They like to attract. So you've also got this electrostatic interaction happening between the positive charge on the amine group of the lysine and the negative charge on the oxygens of the glutamate. So that is also another interaction that's happening within these two alpha helixes. And so for our second discussion, what could we do? What other amino acid could we use instead of leucine that would create a very similar interaction? So when I was looking, I found valine, and it's very, very similar to the leucine, and so I thought that would be perfect. So valine is actually a hydrophobic, nonpolar amino acid, just like leucine, and it's actually only one CH2 group difference between the leucine and the valine. So this valine, two valines, if they come together, they're also going to create that hydrophobic interaction. And then, so that's a amino acid that we could exchange for the leucine that would actually create a very similar effect. So what could we do to kind of break apart that that zipper? So what can we do to kind of mess up that hydrophobic interaction that's holding the two together? I was looking, and I found serine. So something special about serine is it is actually a polar amino acid. So it has an OH group on its R group. So that actually means that it's hydrophilic, so it likes water. So this would kind of break apart that hydrophobic interior because it's hydrophilic, so it's the exact opposite. So those two aren't going to interact. Hydrophobic and hydrophilic are not going to interact because they react with completely different molecules. So that would kind of rip apart that zipper, right? So it wouldn't come together. And then, so what else could we change on the structure that would allow it to react similarly with that electrostatic interaction? So what could we change our lysine and our glutamate out with? And so the best two I found were aspartate and arginine. So I actually drew a little picture because I don't trust the internet. So here we have our aspartate and our arginine. So our arginine on the on this side, we're going to have that NH2 group, and that's going to have a positive charge on it. And that's actually shared between multiple atoms there. And then same thing's happening over here. So at equilibrium, that negative charge could be on either of the oxygens. And so it's shared. So you've got a shared positive charge on the arginine and a shared negative charge on the aspartate. And so same thing, just like with the lysine and the glutamate, opposite charges attract. And so you're going to have these two amino acids that are going to act very similar. So that's my discussion, and I'm looking forward to hearing from everyone else.